So the next is to plot these models and try to compare them. All right, so we now see for the models now in a plot, and we would see how to compare these models. All right, so these are the results we are having in R. So I have brought out the comparisons of this data and place it input it in a PowerPoint so that I can do a brief comparisons between these model. So let's go to our PowerPoint slide. So here is a performance metric summary of our models. So look at the models, their accuracy, their sensitivity, specificity, and their area under the curve. All the results that we would be comparing. All right, so we're having a total sum of 4 models. So let's look at their summary interpretation. So for the logistic regression, just like we stated earlier, this is the accuracy. So the model performs moderately well with the accuracy of 70.65 so comparable to the support vector machine, so but slightly lower than the random forest and the XGBoost. Now the sensitivity here, just like we said earlier, is about 55.26%. It captures some positive cases but underperforms compared to the random forest and the XGBoost. So for the specificity, we have 77.78%. The model performs better for the negative class compared to the sensitivity. The area under the curve, we are having 0.71. So from the table here. So for the logistic, what this implies is that for the logistic regression, we have moderately separates the class. That is, the logistic regression moderately separates the classes, but it is not the most robust classifier in this data set. So conclusion, the logistic regression is interpretable and performs decently, but struggles to balance sensitivity and specificity. So that is for the logistic regression. Let's go to the next model, the random forest. So the accuracy here is 72.46%, slightly better than logistic regression, and the support the SVM, the support vector machine, but marginally behind the XGBoost. Sensitivity is about 70.17%. The model identifies positive cases much better than logistic regression and significantly better than the support vector machine. For the specificity, we have 74.44%, which implies a good performance for the negative class, and the area under the curve is about 0.75. So the random forest demonstrates solid discriminatory power between classes. So we have the kappa, which is here, we have approximately 0.445. So I should mention that for the logistic regression, the kappa here is 0. All right, so let's have that interpretation for the random forest. So for the kappa, it indicates moderate agreement between the predictions and the true classes. So for the conclusion for this particular model is that random forest is a well-rounded performer and balance both sensitivity and specificity better than logistic regression. The essence of doing all this model is to get the model that is better fit for our data. That model would be what we would use to predict type 2 diabetes. Now the third model, we are having the XGBoost. For the accuracy, we are having 73.16%, the highest accuracy among the models. So for the sensitivity, we are having 72.54. XGBoost captures the positive class nearly as well as the random forest. So for specificity, we're having 75.00%, which implies marginal improvement compared to the random forest. So the area under the curve, we're having 0.76, the highest area under the curve value indicates strong class separation. The kappa of 0.50, the XG boost has the best agreement between the prediction and the two classes. So for conclusion, the XG boost outperforms all other models in accuracy, area under the curve, and balancing sensitivity and specificity. It is the best overall model for this data set. So for the support vector machine, the SVM, accuracy is 70.35%, comparable to logistic regression, but lower than random forest and XG boost. For sensitivity, we're having 0%. So the SVM fails to identify any positive cases, indicating a severe issue with class imbalance or model configuration. For specificity, we're having 100%. While perfect for the negative class, this is due to overfitting to the majority class. So the area under the curve is about 0.5458. So with this poor is AUC, barely above random chances. So for a conclusion for the SVM, so we can conclude that SVM is not suitable for this dataset in its current configuration. It suffers from a class imbalance issue and fails to generalize well. So quickly, overall comparison and recommendation. For the burst model, the XG boost emerges as the best performing model with the highest accuracy. So for the second best, we have the random forest, which performs closely to the XG boost, and it is robust. It's a robust alternative with slightly lower accuracy and AUC, but still strong performance metrics. So the logistic regression, while it is interpretable and computationally efficient, it falls behind the sensitivity and overall performance. So the support vector machine, this model performs poorly and is not recommended unless its issue, which include the class imbalance and hyperparameters, are addressed. So for the final recommendation, use XG boost for the best overall performance, particularly if the interpretability is not the primary concern. If computational efficiency or interpretability is important, consider random forest or logistic regression as alternative. All right, so this is the plot we are having. So the plot is called the receiver operating characteristic curve. So the rock curve provides a graphical representation of the performance of the four models across all classification thresholds, highlighting their trade-offs between sensitivity and specificity. All right, so now let's have the interpretation of this. So the blue lines are for logistics, so you can see the colors of the lines for the various model. So the blue rock curve shows moderate performance with a curve slightly above the diagonal. This aligns with the AUC of 0.71, indicating that while the model is better than random guessing, it does not perform as well as the other ensemble methods. Logistic regression may struggle in handling complex relationships in the data. So for the random forest, the red curve lies above the logistic regression curve, indicating better overall classification performance. This is consistent with its AUC of 0.75, showing improved sensitivity and specificity trade-offs compared to logistic regression. So the random forest captures the complexity of the data better than logistic regression. So the next one there is XG boost, which is green, and So the XGBoost, the curve, is the highest among all the models, reflecting its superior classification performance. So the SVM, so for the SVM, you would also see the curve closely hugs the diagonal. So the SVM, it closely hugs the diagonal. All right, so basically that is the analysis of the rock curve. So to incorporate the rock curves into the model comparison, the visual analysis supports the numerical results, with XGBoost clearly standing out as the best model, followed closely by the random forest. Both ensemble methods benefit from the ability to handle nonlinear relationship and complex patterns within the dataset. So for the logistic regression, so it performs reasonably well, but out it is outspaced by the assemble methods in capturing the nuisance of the data. So then the SVM fails to provide meaningful classification performance and is not a suitable choice for this dataset without significant reconfiguration or pre-processing, that is addressing the class imbalance. So for the final conclusion, the rock curve analysis further validates the XGBoost. So it further validates that the XGBoost is the top performing model, with random forest as the strong alternative. Logistic regression is acceptable for simpler dataset or where interpretability is critical, but it lacks the sophistication to compete with the assemble methods in this case. So the SVM, given its poor performance, should be reconsidered only after significant tuning or data adjustment. So these findings, supported by both quantitative metrics and visual evidence, solidify the recommendation to use XGBoost as the primary model for this classification task. All right, so the next step to improve model performance. So we have to address class imbalance. So we use techniques like smooth, which means synthetic minority oversampling technique, class weighting or undersampling to balance the data. Also, we can, for feature engineering, we can add more predictive features or refine existing ones to improve model learning. The third is model optimization. We can perform hyper parameter tuning for random forest, XGBoost, and SVM to improve performance. So alternative metrics, we can also evaluate using precision, recall, F1 score, and focus on metrics like AUC, which is area under the curve, for imbalanced data set. So this is all I'll be sharing for this tutorial. In our next tutorial, we are going to look at how to perform techniques like smooth, which stands for synthetic minority oversampling technique. So stay tuned and kindly subscribe to my channel. Click on the notification button so that you will get instant notification once I upload new videos. Share and give a thumbs up.